students, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, we are going to teach integration of radar pulses, radar cross section of targets. Now, first of all, integration of radar pulses. So, what is meant by the radar? Radar is basically very much useful in the case of a military operations or other activities. We have discussed about that that the radar can be used for the navigation purpose, radar can be used for our medical purposes also. So, one of the important parameters of the radar pulses is the integration of radar pulses. That is the number of pulses, that is basically what happened in the radar. Radar, we used to antenna used to provide the signal to the target, and the frequency which is returned from the target is again received by the target receiver's antenna, and that is and on the basis of the received signal, the radar decides about the position or the type of the target which we have, from which the signal get reflected. So, the number of pulses that is returned from the point target by the scanning radar with a pulse repetition rate of fp hertz. So, what is the here we are going to calculate? Here we are going to calculate the number of pulse that is returned from the point target by a scanning. What type of radar? Scanning radar, and what we are going to calculate the number of pulses that has to be returned. And what is the pulse repetition rate in this case? fp hertz. And antenna beam width, theta b degree, that is basically the antenna of the receiver section, and beam width, the beam which is formed by the antenna, and that is equal to theta b, and which scans at a rate of, or the antenna is scanning at the rate of theta s degree per second. So, the number of pulse that can be returned from the point target is given by theta b, which is the beam width in degree of a antenna, fp, which is the repetition rate, pulse repetition rate, and its unit is hertz, and theta s, that is the scan rate, and unit is degree per second. And if we want to solve it further, theta s can be equal to 6 omega r, where omega r is revolution per minute, and if a 360 degree rotating antenna, the number of pulse received is n is called the hit per scan or pulse per scan. The number of pulse which is returned from a point target is also called as the hit per scan or pulse per scan. So, basically what the information we are getting from this parameter is, this expression is that the number of pulses that are returned from the target depends upon the scanning radar repetition rate, antenna beam width, and the scans pulse. The process of summing all the radar echoes available from a target is called the integration, and when we sum up all the summing of all the radar echoes which are received at the radar is called the integration of radar pulse. Now, the types of integration of radar pulse. So, what we have seen, that what happened whenever the signals come from the point target to the radar, one by one all the signals when comes up and we sum up all, that is called the integration of radar pulse. So, now the types of integration of radar pulse. There are two types of integration of radar pulse. One, that is pre-detection integration, or which is also called as the coherent integration. Second one is the post-detection integration, and it is also called as the non-coherent integration. So, what we have seen, that the radar, integration of radar pulse is further divided into two parts. First one is the pre-detection integration, which is also called as the coherent integration, and the second one is the post-detection integration, which is also called as the non-coherent integration. So, as the name suggests that the pre-detection, that is this integration will occur before the detector comes into account, and this integration comes after the detector comes into account. So, just have a look, integration that is performed in the radar receiver before the second detector, and where the second detector exists in the IF section, that is intermediate frequency section of the radar. Pre-detection integration is theoretically lossless, but it requires the phase of the echo signal pulse to be known and preserved in order to combine the sine wave pulses in the phase without loss. So, what we have concluded from this, that the pre-detection integration occurs before the second detector operation is before the operation performed in the second detector, which occurs in the intermediate frequency section of the radar. Basically, it is considered to be a lossless, but what is it required? It requires the phases of the echo signal to be known and preserved in order to combine the sine pulses in the phase without any loss. That is why it is also called as the coherent integration. But what happens in the non-coherent integration or the post-detection integration? Integration of the radar pulses is done after the second detector, and it is easier to implement than the pre-detection integration since the phases of the echoes are not preserved. So, it is the advantages over that, because here is a constraint in the first one, that we have to preserve the phases of the pulses, but here we are not required to preserve the phases of the pulses, and only the envelopes of the pulses need to be aligned to perform addition. Therefore, it is a theoretically integration with this method. So, whatever we are saying, that there are two types of integration of radar pulses, pre-detection and the post-detection. Pre-detection before the second detector operation and post-detection after the second detector operation, but the difference is that the pre-detection is the coherent integration and the post-detection is the non-coherent detection. The pre-integration, the theoretically it is a lossless system, because here why it is called as the coherent one, because the phase of the echo signal pulses or signals, we have to preserve it and we have to know it in order to combine the sine wave pulses without any loss. But in this second one, that is the non-coherent detection or the post-detection integration, we have not to require to preserve the phases of the echo. What we have to deal first, only we have to envelopes of the pulses need to be aligned for the performance of the addition, that is the integration. Now, the next topic is the integration improvement factor of radar pulse. So, if we have to do the integration improvement factor of the radar pulse, we have to do what? Now, if n pulses all of the same signal to noise ratio were perfectly integrated by an ideal lossless pre-detection integration, the integrated signal to noise ratio would be exactly n times that of a single pulse. This occurs with the pre-detection integration. So, what we are going to see here, that in the case of a pre-detection integration, what is basically happen? If n pulses all of the same signal to noise ratio were perfectly integrated by an ideal lossless pre-detection integrator, the integrated signal to noise ratio will be n times that of the single pulse. n times the signal to noise ratio of a single pulse, and this occurs with the pre-detection integration only. But this is not the exact condition always. If the same n pulse were integrated by an ideal post-detection integration device, the resultant signal to noise ratio would be less than the n times that of single pulse. Now, in the pre-detection, what is the output of the integrated signal to noise ratio? It will be n times that of a single pulse. But in the case of a post-detection integration, the integrated signal to noise ratio would be less than the n times that of a single pulse. This loss in integration efficiency is caused by a non-linear action of the second detector, and already we are aware that the second detector device is a non-linear device, and in the post integration method what is happening? We are performing the integration after the signal comes from the detector section. That is why the non-linear characteristic of a detector section is added to the signal now, and so there is a loss in the integration efficiency of the signal, and for that reason the resultant signal to noise ratio would be less than that of a n times that of a single pulse, which converts some of the signal energy to noise energy in the rectification process. And what is we are saying that the resultant signal to noise ratio is less than the n times of the single one, then what is the reason and where the signal goes? So, the signal will be lost as a noise energy. Now, integration so the integration efficiency terms comes for the post detection integration. For the post in an integration efficiency for post detection integration may be defined as E subscript n bracket n is equal to signal to noise ratio of the single pulse divided by n into signal to noise ratio n times. So, as a signal to noise ratio n 1 is equal to single pulse signal to noise ratio as already told you, or signal to as upon n subscript n is equal to required signal to noise ratio per pulse when there are n pulses integrated with the pre-detection without loss. The improvement in signal to noise ratio when n pulses are integrated is called the integration improvement factor, and it is given by I small I subscript. In the subscript we have small I within bracket n is equal to n E subscript I within bracket n, which is our this term. This is also called as the equivalent number of pulses integrated, and it is equal to n subscript EQ, that is stand for the equivalent, is equal to n E subscript I n. So, the term IIN is called as the integration improvement factor, and it depends upon the this one, and this depends upon the our signal to noise ratio for a single and for the combined one. For post detection integration, what happened? NEQ, that is the equivalent number of pulses integrated, is less than n for ideal pre-detection integration technique. This is here it is less than n. Now comes the radar cross section of targets. The target plays a very significant role in the radar operation. Sometimes it will be our size of the target, sometimes it will be our shape of the target. So, in general we can see the target plays a very important rule, because whatever signal we are scanning, whatever signal we are analyzing in the radar is basically which is reflected from the target. So, now we already know that a radiated power density at the back of the radar, basically we have already aware with this expression, we have studied about this expression. This is the radiated power density, and here P is the transmitted power, G is the gain, P transmitted power, 4 pi is the constant, R is the range. So, here comes the sigma, and this sigma is our radar cross section. So, we can easily say what power we are getting re-radiated back at the radar after getting hit by the after hitting the target is our re-radiated power density, and it depends upon the various factor, and one of that factor is the sigma, with which it is directly related, and it is the radar cross section of the target. So, what happen if basically what we say, radar signal antenna is here, it is giving the signal to the target and the range is R. So, antenna is giving the power Pt and it is having the gain of G, and R is the range of the target. So, target, this is radar cross section of the target. So, once the signal is hitting it and it is coming back, and when it is coming back, it is equal to this one and it is equal to Pt upon G. Pt into G upon 4 pi r square into sigma upon 4 pi r square. So, radar cross section sigma is the property of the scattering object or target, which is included in the radar equation. This is our radar equation. This is a part of a radar equation basically. To represent the magnitude of the echo signal returned to the target by the radar by the target. The re-radiated power density back to the radar is equal to this one. As per the electromagnetic scattering, sigma, which is basically here defined as the radar cross section, is equal to power reflected towards source, that is our radar here, reflected towards source per unit solid angle. Solid angle is basically defined here because whenever we define our power in the case of an antenna, which is basically the receiving and the transmitting section in the case of a radar, is defined in the terms of solid angle, is upon incident power density upon 4 pi, and it is equal to 4 pi r square into reflected electric field whole square upon incident electric field, where R is the range to the target, ER is the electric field strength of the echo signal back that is received at the radar, and this is the EI is the electric field strength incident to the target. So, what is the now? The sigma as per the electromagnetic scattering, sigma is equal to 4 pi into r square. The r square is basically the range between the radar and the target. ER received signal at the radar section after hitting the target, and EI is the electric field strength incident to the target. We can define it in the terms of power also, magnetic field also, but here it is defined in the terms of electric field. Now, sometimes the radar cross section sigma is said to be frictional area that intercept a part of the power incident at the target, which if scattered uniformly in all direction produces an echo power at the radar equal to that of the produced at the radar by the real target. The real target do not scatter the incident energy uniformly in all direction. So, there is a other way of defining the radar cross section, that it should be a fictional area that intercept a part of the power. Is a fictional area which basically receives the power incident on the target, which if scattered, it will scattered uniformly in all direction, produces an echo power at the radar equal to that the produced at the radar by the real target, and it produces an echo power at the radar equal to that of the radar by the real target, but the real target do not incident power uniformly in all direction. So, basically sometimes it is a radar cross section, sigma is also defined as this way. Now, factors on which the radar cross section depends. Radar cross section depends on the characteristic dimension of the object compared to the radar wavelength. So, what is it? Dimension of the object or the dimension of the target compared to the radar wavelength which is incident on the target. So, when the wavelength which is incident on the radar wavelength which is incident on the target is large compared to the object dimension, scattering is said to be a Rayleigh region, said to be in Rayleigh region, when the wavelength is large as compared to the object dimension. In this region, the radar cross section is proportional. In this region, what is happening? Radar cross section is, which is basically defined by the sigma in the equation discussed earlier, proportional to the fourth power of the frequency, is proportional to the fourth power of the frequency. Sigma is proportional to the fourth power of the frequency. And it determined more by the volume of the scatterer than by its shape, and the determining factor here is the volume of the scatterer than its shape. So, just I want you to keep this in mind, because in the next section just the reverse will happen. At radar frequency, the echo from REN is described by this scattering. So, the example of this is at radar frequency echo which is received from the REN is described by Rayleigh by this scattering method. And so, what we have calculated through this, that is Rayleigh region when the wavelength is large as compared to the object dimension, then the scattering is said to be in the Rayleigh region. The important parameter is wavelength should be large as compared to the object dimension. Second thing is, in this case the sigma which is the radar cross section is proportional to the fourth power of the frequency, and it is determined more by the volume of the scatterer than its shape. So, here the most important factor is the volume of the. On the other hand, when the wavelength is small, just the reverse of the Rayleigh region, when the wavelength is small compared to the object dimension, it is said to be in optical region, and in this region the radar cross section is affected more by the shape of the object than by its projected area. In the previous section, in the Rayleigh one, what is we have saying, that wavelength is large as compared to object dimension, but in the optical lambda is less than the object dimension. The second thing is the volume is more significant than shape. Here shape is more significant than volume, and these two are the two most important one. Now, in between Rayleigh and the optical region is the resonance region, the third one, where the radar wavelength is comparable, that means approximately it is equal to the object dimension. For many object, the radar cross section is larger in the resonance region than in the other two region. बहुत सारे cases में what we are saying that the radar cross section is larger in the resonance region. So here is basically a diagram showing normalized radar cross section of a sphere as a function of its circumference measured in wavelength. So this are the region of Rayleigh scatter region and resonance, which is also sometimes called as the Mie region, MIE, and the third one is the optical region. Resonance region lies in between the our Rayleigh region and the optical region. So on summing up the today's lecture, what we have studied about the integration of radar pulses. The integration of radar pulses is decided by the three important factors, that is theta b, fb and theta s, and it is basically the number of pulses that return from our point target by scanning radar. The second one is the two type of integration, that is the pre-detection and the post-detection, and we have studied about the differences which exist in this two type of integration. In the third part, we have come across the integration improvement factor of radar pulses in the case of a pre-detection and the post-detection integration. Then in the next one, we have studied about the radar cross section of targets, which is basically defined by sigma, and on which factors it depends. On the region on basis of which the radars of the radar cross section depends are the Rayleigh, optical and the resonance. We have discussed this. So thank you for attending today's class.